All right. So, particle motion is like a great way that we can kind of start applying this calculus that we've been learning, all right, the concepts of it, okay? And particle motion is exactly what it means. It's like describing the motion of a particle, right? And why a particle? Because we can kind of think of a particle as almost having like no mass, so we don't have to worry about like, and it's frictionless and stuff like that. So we kind of imagine like an ideal environment where like momentum isn't a thing necessarily, and you know, I don't know. Friction doesn't, like I said, it's frictionless and stuff like that. So it's basically like just kind of an ideal environment where you can really just focus like on the pure, position, velocity, acceleration of the idea. So the three kind of main concepts that you need to keep straight initially, right, are the idea of position of the particle. Okay, so like where it is located in space, or we typically think two-dimensionally. We typically talk about like the particle moving along the x-axis or moving along the y-axis or something like that, just to keep it simple. And again, the position typically is written in like as a function x of t, or sometimes s of t as well. It can also be like s of t. Okay, and then the velocity of that particle as it's kind of moving. Okay, and the velocity is directly related to the position. Okay, so we designate the velocity as v of t, but since it is the rate of change of the position, what else could we call it? Well, when we want to talk about the rate of change of a function, what do we do to that function? In calculus, at least. Find the derivative! You got it, Joy. So it'll be x prime of t, like so. Okay? So x prime of t is the velocity, which is also v of t, right? So we take the derivative of that position function, and we get the velocity. Okay? So you can think of the velocity as like the speed of the particle with a direction. Let me put the actual width. Okay, so the sign of the velocity, whether it's positive, whether it's negative, will indicate also what direction that particle is moving. But then the velocity itself will give you the speed. Okay, so speed and velocity are closely related. Speed, though, typically doesn't have a direction, and we'll get more into that, I think. Yeah. Okay, we'll get into what speed. We'll get more of that in just a second here. And then acceleration. So the velocity is how the position is changing, right? The acceleration is how the velocity is changing. So then it would make sense to say, again, we describe the acceleration typically as a of t, and normally t is our independent variable because we're talking about with respect to time, of course. So then what can we do to the velocity to find the acceleration? If the acceleration is the rate of change of the velocity, then that means what can we do to velocity to get acceleration? Yes, oh my goodness, the chorus of voices, I love it. So yeah, v prime of t, or since v of t is x prime of t, how does the acceleration relate to the position then? Second, yes, yeah, x prime prime of t. Okay, just like that. And again, maybe you guys already have this all in your notes. So again, think about this. This is again the rate of change of the velocity. Okay. So let's then fill in some of these blanks because of like all the, because now we're in a context, we now can like use these phrases or words that would make sense in the context to be able to translate these things into math. So for example, right, if we start by assuming that x of t represents the position, which you've already talked about up here, right, position of a particle along the x-axis. So in other words, this particle is moving only along the x-axis. So essentially it's like a one-dimensional motion, right? It's only moving left and right, and that's it. We're not talking up and down, we're not talking like backwards and forwards, we're not talking 3D, we're not talking 2D, we're talking one-dimensional, just moving along the x-axis, left and right, okay? At any time t, then this means what? So initially would mean when what would be equal to 0? Well, initially would be when we start, right? At the start, so that's when time would be 0, okay? At the origin then, so if the particle is at the origin, well, that would mean its position. So that would mean that x of t, the position, would be equal to 0 because we're starting at the origin, right? Oh, hello, Sion. Okay. And then at rest, At rest would mean the particle is not moving, right? Not moving left, not moving right. It's staying still. That means its velocity would be 0. Okay? It might be at rest, 3 units away from the origin, right? So its position doesn't have to be 0 when it's at rest, but it's not moving, right? Your car is stopped, right? So that means you are your speed, or in this case, really, we talk about velocity, is 0. Okay. Number 2, if the velocity of the particle is positive, okay, so that's a direction, right? If we're on the x-axis, right, moving along the x-axis, velocity is positive. What would make sense to say then that, what direction would it make sense to say we're moving? Well, moving to the right, right? If we're moving on the x-axis and it's a positive direction, then intuitively, I hope you guys would think that we'd be moving to the right. And then if the velocity is negative, the particle should be moving to the left. Okay, same kind of idea. And we can only tell these specific directions because we know our particle is moving along the x-axis. Okay, if the particle were moving along the y-axis, then a positive velocity would indicate what? If the particle is moving along the y-axis, then what would a positive velocity indicate? What direction would that particle be going? Anybody? Yeah, exactly, up. And if it was a negative velocity, it would indicate going down, right? Okay, so you just want to pay attention to all these little details here. Every little piece of information here is pretty important to, at least recognize and stuff. All right, number 3, to find the average velocity. Okay, so average. We've heard that word average before, right? We've heard about that as the average rate of change, right? So if we want to find the average velocity, well, we know if we want to find the average rate of change, okay, that's going to be using the slope, right? Slope formula. Okay, well, average velocity, well, think about velocity then. What is velocity the rate of change of? Velocity, if we go back up here, right, to our relationship between position, velocity, and acceleration, what is velocity the rate of change of? The position. So instead of saying average velocity here, and maybe I shouldn't put an X through that, but I mean, instead of saying, actually, no, I'll do this. Instead of saying velocity, I could say average rate of change of position, right? Those are synonymous. They are exactly the same concept. Velocity is the rate of change of the position. So when I see average velocity, I could also say average rate of change of position, which we know how to find an average rate of change. It's the slope formula. So divide the change in the what? If we're trying to find the average rate of change of position, we want to divide the change in the position, which might throw some of you guys off because you're like, whoa, 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 Mr. Bid, pump the brakes. You said average velocity. Why are we finding the change in position? Well, I'll show you. Let me get through the rest of this here, and I'll explain why. So position by the change in time. This is the average rate of change of the position of the function. Okay. So why is it that we divide the change in the position by time and we end up with an average velocity? Well, think about this, right? If I do x of b minus x of a over b minus a, this subtraction up here is going to be some sort of position. So let's just say we're talking like meters or something like that. Right? Meters could be like a description of position. And then b minus a, those are times, right? And so the b minus a is going to give us something in time. And you see by doing this change in the position divided by the change in time, what do we end up with? We end up with units in meters per time, length per time, which is a velocity unit, right? You think about like, your car, right? When you drive it, it's miles per hour. It's a distance over a time. That's a velocity unit. And so we end up with a velocity unit this way. If you were to try to do, v of b minus v of a over b minus a, well, your top units here would be like, again, let's just say like for the sake of this, meters per second, divided by further by seconds. And meters per second divided by seconds would yield meters per second squared, which those of you that maybe have taken some physics or something like that, what kind of unit does this describe? Or not kind of unit, what kind of function, what kind of quantity or concept does this describe when you have meters per second squared? Yeah, this is acceleration. Okay, so watch out for this is what I'm trying to say. Okay, and in fact, we'll talk about, I think we talk about the average velocity, right? No, we don't talk about average velocity. But that would be how you, oh no, there it is, average velocity. We don't talk about finding, anyway, average acceleration, stuff like that. So that's how you would find average acceleration. Okay, that's a separate thing. Maybe I should kind of move this over somewhere. Oh, there we go. It doesn't want to move for me. Okay. So anyway, okay. So when you want to find average velocity, right? Watch yourself, right? You really want to find. You're going to use position in the formula. Okay. Later we will find a way to find the average velocity and then use the velocity. Okay. So I know it's kind of weird that we're asked to find the average of something and then we use its position, not its velocity. Okay. So just keep that in mind. Later we will, but it's going to be until like several units down the road kind of thing. All right. Instantaneous velocity is the velocity at a single moment or instant in time. Okay. So this is the instantaneous rate of change, aka how do we find the instantaneous rate of change? It's the derivative. Okay, of the blank function. Well, again, if we're trying to find the instantaneous velocity, right, we're trying to find the derivative of the position function. Okay. Okay, because it is the derivative of the position that yields velocity, right? So there's that. Okay, if the acceleration of the particle is, so here's now talking about acceleration. If the acceleration of the particle is positive, then the velocity is increasing. If the acceleration of the particle is negative, then the velocity is decreasing. Okay, think about it this way, right? When if you guys are drivers, or if you've ridden with your parents or something like that, right, in a car, and you guys are like going to get on the highway, right? You have those acceleration ramps to speed your car up to get on the highway, right? So when your velocity is increasing, right, you have to increase your velocity from wherever you are to the highway speed, right, highway velocity of 55 miles per hour, whatever kind of thing, or 60 or 70, whatever it happens to be. Then you have to accelerate, right? You have to increase your velocity so you have positive acceleration there because you're speeding up. But then when you get to a stoplight or something like that, you want to decrease your velocity down to 0 so you can stop at the stoplight, not hit somebody, right? And that's a negative acceleration. And you might also call that a deceleration too, right? Anyway, number 6, in order for the particle to change direction, so what thing determines the direction the particle moves? Again, which of these functions, position, velocity, acceleration, describes the direction the particle is moving? Right, so then if we want to know when very good, Basil, yes, exactly right. If we want to know then when the particle is changing direction, that would mean the velocity must change signs, right? If a positive velocity indicates you're going one direction, and I used to stop there and say, oh my gosh, one direction, but I don't know if people really love one direction anymore. So anyway, and then if you have a negative velocity, you go the opposite direction, right? And so velocity changing from positive to negative or negative to positive, then you have to change signs, okay? Speed, all right, is related to velocity, but it's not the same idea. So be careful about that. I don't want to use those things interchangeably. Speed is the absolute value. Speed, that's right. Speed is the absolute value of velocity. Okay, so if you think about, on the highway, for example, right? If you're driving 55 miles per hour down the highway, you say you're driving 55 miles per hour, right? If you were driving 55 miles per hour down the highway, but you're driving backwards, you're still driving 55 miles per hour, okay? That's how you would describe it. So you're describing your speed, right? So watch out for that, right? If you drive forward at 5 miles per hour, if you drive backwards at 5 miles per hour, you're still saying you're driving 5 miles per hour. You're describing your speed, okay? Absolute value of the velocity is the speed. So speed eliminates the direction component of the velocity, okay? The amount of ground the particle covers, okay, is the distance. Okay, the change in the final position and the initial position is called the net displacement, or sometimes just the displacement. Okay, so I'm going to put net in parentheses. Sometimes it's called net displacement, sometimes it's called displacement. Okay, and that's only final position, take away the initial position, right? It's the change from the final to the initial position. All right. So for example, if Mr. Wid, normally I would do this in person, right? But I can't really do that here. But if I stepped, one step left, wow, I drew left, but I really moved myself right, but I was pretending like I was facing you guys, so to me, if that stick figure is facing you, that would be a left. Strange. Anyway, if I stepped one step to the left, like they say to do in Mambo number 5, right, but then I stepped one step right back to where I was, my net displacement would be 0 because I started and stopped in the same position. Yes, exactly. Okay, so I started and stopped in the same position. Okay, however, if you think about that, I really traveled, 1 unit left and then 1 unit right. So that'd be 2 units, but we have a different concept to describe that. That's called total distance traveled, and we'll talk about that later. But right now, if I step 1 step to the left and then back 1 step to the right in my original spot, I would say my net displacement is 0 because my start and my stop are the exact same points, even though I have traveled some in between. So keep that idea there, kind of in your head too. That net displacement, it doesn't mean how far you've traveled. It means what's the difference between where you started to where you stopped. And if you start and stop in the same spot, then your net displacement is 0. Finally, number 9, particle speed is increasing when the signs of the velocity and acceleration are the same or equal. Okay? The particle speed is decreasing when the signs are opposite. Okay, and this might make sense to you, so in some sense, there's like an intuitive sense, right? So for example, if you have a positive velocity, okay, if your velocity is positive and acceleration positive, then that kind of makes sense that, yes, we're speeding up. Okay, and it might also make sense that when the velocity is positive and your acceleration is negative, right, like a deceleration, right, then we're speeding down, I guess we'll say. Okay, but what might be a little bit weird to think about is that if your velocity is already negative and your acceleration also happens to be negative, then that would really mean you're also speeding up. Okay? And so you can kind of think about it, well, I would draw a graph, but I don't know if the graph's going to be super helpful. But if your velocity is already negative, right, so I mean you're traveling some certain distance to the left, we'll say, traveling some certain rate to the left, then your acceleration is also negative. That means it's making this velocity more and more negative. So the velocity is getting further and further away from 0, right, in a negative direction. So maybe the velocity started out negative 10, but since your acceleration is also negative, it's going to go to like negative 11, negative 12, negative 13, your velocity is. You're going to get further and further from 0, which means you're not going to get slower, right? Your velocity is speeding up. You're increasing your rate in a negative direction, so it's just going the opposite direction kind of thing. Whereas if your velocity is negative and your acceleration is positive, well, now the acceleration that's positive is trying to counteract that negative velocity. So it's making the velocity less and less negative since the acceleration is positive, bringing it closer and closer to 0. And a 0 velocity would mean your speed is 0. So in other words, you're speeding down. Okay, so these are maybe the more weird ones here because you have to like think about in terms of velocity with its direction idea and not as so much as speed. So anyway, keep that in mind. Okay. All right, questions on any of that? We're going to get into some actual application problems here, which might be more helpful than just like this information dump. Okay, so any other questions before I move in? Okay, let's do this then. So number 9, we actually have a problem here. The data in the table below, and this is very important to read this kind of introductory information as well. When you guys do these problems, sometimes I know maybe in your previous math classes you just kind of glossed over that. You're like, yeah, okay, I'll just kind of like skim it. Read it because there's important information here that you might need to use. So data in the table below gives selected values for the velocity in meters per minute. So units are important for these questions too. Oftentimes you want to make sure you're including units. You can lose points sometimes for not including appropriate units. Of a particle moving along the x-axis. Okay, so we're moving left and right. The velocity v is a differentiable function of time t. So differentiable, that means we are able to differentiate it, right? So in other words, we can find the acceleration. And acceleration should exist everywhere for some time t. Okay, and then there's our table. Okay. At time t equals 0, is the particle moving to the left or to the right? Sorry, I read it backwards. To the right or to the left? Well, what do you guys say? Look at the table there. What would you say? Is the particle moving to the right or to the left? Sorry, my son is not having a good time right now. To the left? Okay, justify or explain your answer, please. Exactly right. That's all you really have to say there, okay? So you could say here, yes, Basil, exactly right, okay? So you could just say something like left because v of 0 is less than 0. That's it, okay? That's all you have to say. Like when I, kind of like complain to you guys about some of your justifications, or not complain, but when I give you feedback about your justifications for like continuity and stuff like that, this is all the justification you need to give for a problem like this, how to justify it, okay? Velocity at 0 is less than 0. Okay, that's that. Letter B, is there a time during 0 less than or equal to t less than or equal to 12 minutes when the particle is at rest? Explain your answer using correct mathematical language. So again, looking at our table of information right here, would it seem like our particle should be at rest sometime between 0 and 12 minutes? So why don't you guys think about that one? Don't answer it just yet out loud or in the chat. I'm going to start calling on some folks. Okay. Oh, I'm muted. I was muted the whole time there. I'm so sorry. I don't know how that happened. So sorry, let's look at letter B here. Is there a time 0 less than or equal to 12, less than or equal to t less than or equal to 12 when the particle is at rest? Explain your answer. And what I'm going to do is I want you guys, don't answer it out loud or in the chat. Think about that right now, letter B, how you would answer it. Okay, and I'm going to randomly call on someone. Now, when I call on people, if you are panicking right now because you're like, oh, I hate this, then you can say pass, and you don't have to answer. That's fine, okay? But I also want to give people a chance to answer that maybe want to answer or would be comfortable answering, but like don't like having to like shout it out in the middle or something like that. So you can totally say pass if you want to. I just use my graphing calculator here to pick a random number, and I have you guys. Oh, I thought I had you numbered. I don't have you numbered. Let me do that real quick. So again, think about this question, how you would answer it. Must the particle be at rest for some time t here in this interval? Oh, goodness. He's a cranky boy. All right, 123. All right, so actually, Joy, you're up. What do you say, Joy? Letter B. Is there a time? Okay. Okay. You're... Uh-huh. Mm-hmm. Because why? What theorem are we talking about here? Ooh, it's one of our big theorems we talk about, intermediate value theorem. And you actually don't need to name drop the intermediate value theorem here. Since you said what you said, you've essentially established the criteria for the intermediate value theorem here, and you can then say what you did. So like what you said was perfectly fine without name dropping intermediate value theorem, okay? In fact, you did it a better way. Sometimes students will just say, yes, because intermediate value theorem. And that's not quite right. You need to kind of establish, like Joy did, the criteria for being able to use intermediate value theorem. We have to just say that the function is continuous. But Mr. Witt, it says it's differentiable. Yes, exactly. It says it's differentiable. It does not say it's continuous. You have to make that jump from saying since v is differentiable, therefore v is continuous. Okay? And then we can talk about that here. Okay, so let me show you what I mean by that. So something like and notice here, it's is there a time? So we're talking about existence, right? And the only thing that we've got that helps us prove the existence of something right now is the intermediate value theorem, right? So think about that too. Okay. So first of all, we want to establish v of t, and this is like, again, I'm trying to give you like the best kind of justification. V of t is differentiable for any time t, or we can say v of t is differentiable, so v of t is also continuous. Okay, since differentiability implies continuity, right? Okay. Thus, oh, and actually also we'll say this. Since v of 0, right, the velocity at 0, which is -3 there, is less than 0, and v of 2 is greater than 0, then there must be some time and we'll say like C, sometime C, and I'll say like here 1 or 0 less than C less than 2, such that V of C equals 0. Okay, just like that. Okay, so what did we do here, right? We see here that we want to try to identify there's a time between 0 and 12, right, when the particle is at rest. All right, so many of you guys may be able to like say, oh yeah, we're going from -3 to 2, right? Yes. So many of us hopefully were able to come up with the idea that yes, that is so, right? But then that's part of it, right? But then your justification, and that's where the real fine tuning has got to come in here for our AP calculus class, right? For like a normal calculus class, if it wasn't AP, right? If it was just like, you know, whatever, just we're learning calculus, you know, you could probably provide a little more of like a loosey-goosey definition here. But for our purposes, for the AP test, right, trying to provide good explanations to the AP graders so they can show that you really know what you're talking about, this would be the kind of justification you want to say, okay? In order to use intermediate value theorem, we need to have a continuous function. So we were told it's differentiable, so therefore we can also say it's continuous, right? So check that box. Then we say essentially what Joy said there, V of 0 was less than 0. Okay, V of 2 is greater than 0, right? So we're less than 0, and then we go greater than 0. Then there must be sometime C, and again, we just make up a number C between that 0 and 2 right up here, such that V of C equals 0. Okay, and that is basically restating the intermediate value theorem, but not just name dropping it, right? You're actually like restating it using the actual like words of it and stuff like that. Okay. Questions on any of that justification stuff? Joy, you did a great job there. You really did. That was good. You like went right to the continuity thing, which I think a lot of people might have skipped over, so that's good. Okay. All right. Let's go to letter C then. And again, if you have questions, just stop me, say something. On letter C, what is the average acceleration of the particle over the interval 2 to 5? Okay, anytime you're asked for an average acceleration or average velocity, right, you should always have an interval because we need to use, what formula do we use to find the average of something? An average rate of change. Slope, that's right, Maya, okay? So this average acceleration, we can also think of this as the average rate of change of velocity. Right? Because the acceleration is the rate of change of the velocity. So if we want to find the average acceleration, that's the same thing as finding the average rate of change of the velocity. And like Maya said, that's the slope formula. Okay? So since we're trying to find the rate of change of the velocity, oh boy, too much deleting. Since we want to find the rate of change of the velocity, then what function should I use in my numerator, right? I already know that 5 minus 2 will be in my denominator, and I'm going to do something of the 5 minus something of the 2. What function should I be using in my numerator, though? Oh, let's go to Sarah. What do you say, Sarah? What function should we use in the numerator there? It is velocity. Good job, because we're finding the average rate of change of the velocity. Okay, and then how do we evaluate V of 5? How do we evaluate V of 2? Where do we go to? I'll pick somebody else, Sarah. Good job, though. What can we do to evaluate that? Charlie, what do you say? How do we evaluate V of 5? How do we evaluate V of 2? Look at it. What's it? Yeah, 5, 3. Oops, sorry, and 2, 2, right? So at 5, we're at 3. At V of 2, we're at 2. So it's 5 minus 2 there. So we get 1 over 3. Okay? Show the computations that lead to your answer. There it is. And indicate units of measure. All right, so Charlie, good job there. Go to somebody else. So what would my units of measure be here, Adam? In the numerator, for example, what are my units of measure for the velocity in this problem? What do you say, Adam? Units of measure for the velocity. Okay, fair enough. By the way, guys, I know that maybe like chat is more comfortable, but the longer we stay in here, the more difficult it's going to be to chat in answers too. You're going to have to eventually be able to use your microphone. So if you're like listening to music while listening to me, or watching a TV show, or watching a movie while listening to me, okay, you know, or if you're just distracted or whatever kind of thing, that's, you know, just I would encourage. And I'm not saying that Adam's doing this, but I'm just saying in general, right? You know, it'll be helpful for you guys to actually use your microphones and stuff to describe things, because it's going to be hard to type some of this stuff in. All right, how about Sion? How about you for the average acceleration? What would you say? What would be the units for the velocity here? Any ideas? Sion? Okay, we'll try moving on here to Luke. Luke, help us, Luke. What would be the units here? Okay, for the velocity, perfect. And then the time, what would the time units be? Yep, minutes. And so then meters per minute divided by minutes would give us then 1/3 meters per minute squared. Okay, good job, Luke. Thank you, sir. So there is our average acceleration. Average acceleration. Adam, does that make some sense now? Do you see where those numbers came from? Again, we're just told right up here, meters per minute, time, minutes. Okay? Got it? Good. Okay, awesome. Perfect. Thank you. All right, and then letter D, use the data from the table to find an approximation for v prime of 10 and explain the meaning of v prime of 10 in terms of the motion of the particle. Show your work, indicate units of measure. So any ideas on this one? If we want to find v prime of 10, if you look up here, right, we don't even have 10 listed, right? 10 would be like right here. So how can we use that fact to help us find v prime, the derivative of 10? If we're going to estimate it, right? What would be a good way to maybe try and estimate v prime of 10? Any ideas? Yes, between what two values? Yeah, exactly, right? If 10 is between, right, the time 10 is between 8 and 12, right, and we're trying to find v prime of 10, v prime would be the derivative of velocity, right, which is the slope of the velocity, right, derivative of the slope, right, instantaneous rate of change. Well, we don't have a way to find the slope at 10, but what's a good approximation? If you remember, Sarah said earlier in a previous lesson, right, the secant slope, right, which would be the slope between these 2 points, where 10 is kind of stuck in between there. So exactly right, Greg. Great job. Okay, so we'll say, you know, we'll say v prime of 10 is approximately equal to, squiggly equal sign for approximately, right? We'll say v of 12 minus v of 8. Is that what it was? I gotta check here now to see. Yep, over 5 minus, over 12 minus 8, like that. And then the 12 was 5. Yep, minus 7. And 12 minus 8 is 4. So we get negative 2 over 4 or negative 1/2. Okay? So there's the slope. The units of measure, right? We did velocity divided by time again. So it would again be meters per minute squared. Okay? So there's our answer. Explain the meaning of v prime of 10 in terms of the motion of the particle. So how might we describe this here? There's a couple different ways I could think about it. Okay, so we could say, for example, the acceleration of the particle. Mr. Wade talking about acceleration, but it says v prime. Remember, yeah, v prime is the derivative of the velocity. And what is the derivative of the velocity? It's the acceleration. So that's why I can talk about acceleration here. The acceleration of the particle at t equals 10 seconds is approximately negative 1/2 meters per minute squared. Okay, so there would be one way you could describe the meaning of v prime of 10 in terms of the motion of the particle. Does anyone have any other ones that they thought of that they want me to, like, you know, vet for them if they're like thinking, oh, I thought it might be this too? Anyone else have any other ideas about how to describe it? Okay. Ooh, now that I'm reading that question, though, it does say, explain the meaning of v prime of 10 in terms of the motion of the particle. So that, to me, I'm not so sure if they want us to describe the v prime our approximate or if they want us to describe v prime our exact. Explain the meaning of v prime of 10 in terms of the motion of the particle. I feel like maybe we're supposed to describe just v prime of 10. So this is the meaning of the approximation, right? So this describes this approximation here. But if we want to describe v prime of 10, this would be, you know, v prime of 10 is the acceleration of the particle at t equals 10 seconds. So there would be the actual, I think that's what we're really supposed to do there, is describe what v prime of 10 means in terms of the motion of the particle. But that describes our acceleration too. Okay, questions on D. Oh, it's time in minutes. Oh my goodness, thank you. Yeah, there I go. I said minutes up there and then I put seconds. Sorry. Thank you, Hazel. Keeping me honest. There we go. Okay, perfect. All right, letter E. Is the particle strictly increasing? Is the particle strictly increasing from 6 less than t less than 8? Okay. Is the maximum velocity of the particle at t equals 8? Or is the maximum velocity of the particle at t equals 8? Explain your reasoning. Okay, yeah. So, is the particle strictly increasing from 6 less than t less than 8? Okay. So I think that would mean, is the particle's position strictly increasing from 6 less than t less than 8? So if we look up here, between 6 and 8, right, the velocity is positive 5 and positive 7. Is that enough information for us to say that between 6 and 8, the particle will only ever, you know, its position will only ever be increasing? You know, the velocity is positive here, so it's moving to the right, right? Can we say, since at time 6 the velocity is 5, at time 8 the velocity is 7, can we say for sure then that the velocity will always be carrying us away to the right, based on just these two pieces of information? And this one, again, maybe I'll leave open to you guys to say here. What do you think? John's unmuted, but he's hesitant. Oh, he's muted again. No, he decided not. Justin says not necessarily. John, is that what you say? Oh, I couldn't hear you. No, sorry. It was kind of fuzzy and then it stopped. Basil says no, not necessarily, because we don't know how the rest of the function behaves outside the points given to us. Yes, Basil, exactly right. Ding, ding, ding. Okay, we have no idea, you know, between 6 and 8, right? We don't know what happens. The function, you know, so yes, at 6 we could say it's 5, and at 8 we could say, you know, it's 7. Okay, John, gotcha. Perfect. I'm sorry we couldn't hear you. I don't know what the issue was there. At 6, you know, we do have to go from here to here, but that doesn't mean we can't go down and then back up and then back down to get to those 2 points, right? So that's, we don't know, right? We just can't say. So we'll say not necessarily. And just like Basil said, because we do not know what happens to v of t for t values for times between 6 and 8. Okay, so this question, right? It's not saying, you know, must there be a time when the velocity, for example, is negative, or will the velocity always be positive, kind of thing. All right. it's saying, you know, it's saying must there be a time. It's saying like, does it have to be positive the whole way through, right? That's what letter E is saying. And we can't say that, right? Which is different than letter B, where we said, is there a time when the particle's at rest? Well, yes, like Joy said, right? We go from negative to positive. We have to go through 0. But here, we only know that we have to go, you know, from 6 to 8. We only have to go from 7 to 5. But that doesn't mean we couldn't go down below 0 or, you know, way up above 0 kind of thing. So, Megan, did you have a question, or did you just accidentally unmute yourself? Ha! Okay, there you go. Gotcha. All right, so next, let's go here. So any questions on any of this, on this one right here? I went a little bit slower with that one. Any questions on this one? Okay, cool. Let's keep going then. All right, number 10. The graph below represents the velocity v of t in feet per second. So no longer do we have a table, now we have a graph describing the velocity, right? So we can actually like see what's happening between all the points here. Of a particle moving along the x-axis over the interval, time interval 0 less than or equal to t less than or equal to, now we're in seconds, okay? So, again, let's take a look at this graph, right? At time t equals 4 seconds, so here's t equals 4, okay? Is the particle moving to the right or to the left? Again, remember we are looking at the graph of the velocity here. Okay, so take like a couple seconds there and think about that. At time t equals 4, so here we are, there's t equals 4, right? On the graph, right, is the particle moving to the right or to the left? And be prepared to explain your answer. And I'll call on someone here, so take yourself some time. Okay. All right, AJ, what do you say? Go to the right. How did you know? Okay, so you said it correct. You said the correct direction, but your justification, we need a little something here. How does the velocity tell us the direction of motion of the particle, right? Remember, the velocity has a direction to it. What about its velocity, right? So the velocity at 4 is, we'll say 5, right? So velocity at 5 right there. What about that 5 velocity indicates that we're moving to the right? And it's not because we are just moving to the right here. So if you're not, you want to, like, you have another idea, or you want to pass along someone else? All right, pass it off. Very good. Moving to the right. Adam, can you help him out? So we got the first part. Particles moving to the right because... Any ideas, Adam? Silence. Okay, we'll go to someone else. Let's go to Tyson. What do you say, Tyson? Oh, there it is. It is because, like, as the time increases, the line keeps moving to the right. So that's kind of what AJ was saying, I think, and that would not be the case here. So, you know, as time goes on, right, we are moving to the right, but it's not the graph that's moving to the right, it's time that's moving to the right. As time increases, right, that is what you're saying is moving to the right. Okay? You're saying as time increases, that's our right motion there. But that's not what describes why the particle is moving to the right. So let's go to somebody else here. Let's go to Tyson. Tyson, do you have an idea? Why is the particle moving to the right here? What about the velocities indicating the particle is moving to the right? Ding. Okay, but at time 4, what is the velocity? 5, so that is positive, right? So boom, that's it. Boom. At time t equals 4, the particle is at that instant. And so I think I see what you guys are kind of getting at here, right? You're kind of doing like a general overview of the motion of the particle. But remember, with calculus, right, we're talking about an instant. At time t equals 4, not what happens before 4, not what happens after 4. At time t equals 4, at that instant, the particle is moving to the right. Why? Because v of 4 is greater than 0. Or you can say v of 4 is positive, or you can say the velocity at time t equals 4 is positive. You know, a couple different ways to say that, but you have to, you know, include that you're saying the velocity at that time t equals 4 is positive. Okay? And do not use a plus sign to describe positive. Plus signs do not have that meaning, right? We don't use that. You can't use that as like an abbreviation for positive. Don't put POS as positive, the word positive. Okay, and again, not because I don't know what you mean, but because the AP grader, when they grade your test, they want to know, okay, what does this person mean by that plus sign? Okay, so use the word positive. All right, Adam, does that make sense? AJ, does that make sense about what you guys are missing there? Yes, Adam says. AJ, you're okay now too? Does that make some sense to you? Okay, thank you. All right, letter B. Over what time interval is the particle moving to the left? Okay, so we just finished talking about the velocity helps us determine that the particle is moving to the right at time t equals 4. What is the interval when the particle is moving to the left? So again, think about that for a couple seconds, and I'll call on someone here. Look at the graph. What about the velocity is going to tell us when it's moving to the left? And what is the interval then when the particle is moving to the left? All right, so think about that. We'll call on someone here. All right, let's go to Caroline. Caroline, what do you say? Okay, so when what is 0? When the x is 0, so you're saying like right here, the particle's moving to the left? Aha, when the y is 0, very good. So at what time is the y 0? Okay, and then what's the interval then? So we'll say it starts moving to the left at 5, and then 5 to what though? 6, yep. You can expand that a little bit more. So, no, not the point. I mean the time. There's more times. You can go further than 6 and still be moving to the left. Yep, exactly, 9. Because the velocity is negative over this entire interval, right? We're looking for when it's negative, not when it's decreasing. Okay, when the velocity is negative, that means our particle is moving to the left. Okay, so for 5 less than t less than 9, and I'm going to put less than or equal to 9 because at 9, well, yeah, okay. We can include or exclude that 9 there, but we should definitely exclude the 5, right? Don't include the 5. Because are the particles moving to the left? Because the velocity is, and again, fill in the blank, the velocity, because the velocity is what? Anybody. Negative, not careful, not decreasing, negative. Decreasing indicates something about the acceleration, and we'll maybe get to that in the future. Just the fact that it's below the x-axis here, it's a negative, all the y values here are negative. That's what we want to say. So because velocity is negative on that interval. Okay. Find the acceleration of the particle. Okay. How does the acceleration relate to the velocity again? We have the velocity. How does the acceleration relate to the velocity? It is the what of the velocity? Derivative. That's right, Sam. So we're going to find the derivative of the particle at these 4 times. Okay, so let's focus on time t equals 2. Okay, so looking at the graph there, what is the derivative of the velocity at time t equals 2? I'll like this point right here. What's the derivative of the velocity at time t equals 2? Okay, it is 2. How'd you get that? Yeah, rise over run. Yeah, exactly, right? This is a linear part of the graph, right? And so at this point, if we want to find the slope, I can just count it, right? Up to right 1 or down to left 1, right? So yeah, we can say in here that a of 2, which is really the same thing as v prime of 2, right? And that's what Sam was using there. V prime, right, is the derivative of v is the acceleration. So if we find the slope of v at 2, that's the same thing as acceleration at 2, and he said that is 2, okay? And it would be, again, if we want to use units, it would be like 2, feet per second. Okay, it didn't say to use units, so we didn't have to there. All right, what about A of 3? That would be the same as V prime of 3. And when we see behavior like that on our graph, what does that indicate? It's pointy, right? Charlie? So not 0. 0 would be if it was a nice smooth transition like this, and yes, Charlie would see that. So Basil, yes, does not exist. Because from the left, the slope is a positive 2. From the right, the slope is like -4. 1, 2, 3, 4, 5, -5. We suddenly change here. From the left, it's a positive 2 slope. From the right, it's a -5 slope. Okay, and so then the overall limit here won't exist, right? Because the left and the right hand derivatives don't agree, right? And so the overall function is not differentiable at 3. Okay, velocity is not differentiable. So in other words, it does not exist. Okay, now what would that look like in real life? Well, I couldn't say that. I don't know. Maybe the thing like bounced off a wall or something like that. I don't know. Okay, or no, not even that. It'd be like the brakes were applied suddenly, I guess, kind of thing. At a constant. Anyway, I'm not sure exactly, but anyway, that's there. All right, last one. Oh no, we have 2 more. A of 4, which is V prime of 4. Okay. So go ahead at V of 4. What would that slope be? Or V prime of 4, I should say. -5 feet per second. Again, it's linear, right? So we can just count the slope. And then one more, A of 7, which is equal to V prime of 7. Okay, what would its slope be? Here's 7. All right, let's go to some. I'm going to call on someone for this one. Let's go to John. Hopefully the microphone works this time, John. What do you say? What's the slope there of the velocity at 7? It is 0, and I could just barely hear you through the static there. Don't know what was going on. But anyway, there you go. Yeah, perfect. There it is. 0. Wonderful. Is your notebook on your keyboard or something like that? Maybe that's what it is. Kind of sounds like it. Anyway. All right. Letter D. Is the particle speed increasing or decreasing at time t equals 4 seconds? Okay, so this one I'm going to give you a quick refresher. Right? Remember that these are the situations where how we can talk about whether we are speeding up or slowing down. Right? When the velocity and acceleration are the same sign. Oops, not equal, they should be the same. I think that's probably a better way to describe that than equal. Sorry about that. I now realize that equal doesn't really make sense about equal signs, the same. Okay? And when signs are opposite. So when the signs of the acceleration and the velocity are the same, okay, we are speeding up, right? So if they're both positive or if they're both negative, right, both situations they speed up. If they're opposite signs, then we are speeding down or slowing down kind of thing. Okay? So there we go. So looking here at time t equals 4, okay, we describe the velocity, we describe the acceleration at time 4, right? And then at time 4, we also know the velocity is positive 5. So the velocity at time 4 is positive 5. The acceleration at time 4 is negative 5 feet per second squared. Whoops, these should all be squareds too because they are accelerations. Okay. So back to this. Velocity at time 4 is 5. Acceleration at time 4 is negative 5. So are we speeding up or are we slowing down? Slowing down, Charlie, exactly right. Because why? Can you give me the justification for your answer? How'd you determine that? Yeah, exactly right. So we'll be a little more specific. We'll say speed is decreasing because velocity, we'll say v of 4, is greater than 0, but v prime of 4 is less than 0. And that's all we have to say. Okay? We could also maybe be a little, I can maybe be a little more specific with something like, I could say like v prime of 4 equal to a of 4 is less than 0, like that, okay? To establish that v prime that we had calculated earlier was the a, which I kind of already had there anyway. But that's it. That's all I got to say. The slope of the velocity is negative? Yes. Yes, at that point. Yep, you can absolutely say that. Just make sure you specify the slope of the velocity. If you just say the slope is negative, specify what you're talking about the slope of. But yes, absolutely, sir. Yep. Letter E, what is the average acceleration of the particle? Okay, again, average acceleration. Okay, we don't have an average formula. We have an average rate of change formula. So this wording of average acceleration, we don't know how to find average acceleration yet. Okay, because we don't have an average formula. We have an average rate of change formula. So I have to change this idea of acceleration into a rate of change of something. Okay, what is acceleration the rate of change of? So the rate of change of what gives us the acceleration? What could I change this idea to be? Yes, exactly right, Sophia. Great, exactly. Average rate of change of velocity. And again, I'm just trying to help you guys out here with knowing what to do, right? Because when you see average acceleration, you might think you need to do like a of 4 minus a of 2 over 4 minus 2. But that is not right. Because that formula you just did there would be for the average acceleration. Or sorry, average rate of change of the acceleration. But we are not asked for the average rate of change of acceleration. We're asked for the average acceleration. Not how it's changing, not how the rate of change of the acceleration, just the average acceleration. We don't have a formula yet for the average acceleration, right? We do have a rate of change, or a formula for the average rate of change of something. In this case, we'll do the average rate of change of velocity, so that's the same as acceleration. So, average rate of change of velocity, okay, which would be then v of 4 minus v of 2 over 4 minus 2. Okay, and if you're still like Mr. Wade, your description makes me even more confused, please stop. All right, here's another maybe easier way to kind of check yourself, right? If you know you're trying to find an average rate of change of a velocity, that means your units need to be velocity units. Velocity units will always be distance per time. Okay, so oh, sorry, here. We're trying to find the average acceleration. I'm sorry. Average acceleration will be, well, that is average velocity units. Gracious. All right, let me start over. If you're having difficulty here, determining, what you're supposed to do with the average acceleration, when you see that, when you come across the problem, okay? An acceleration, because we're trying to find an average acceleration here, you can think about, I need units. My final units need to be in distance per time squared. All right, that's an average acceleration. So will I get that here? My velocity is going to give me a distance per time. I will divide by more time. And so then, yes, I will get distance per time squared here in the end. Okay, so let me show you again. So v of 4, we have to go back up here to the graph. So v of 4 we said was 5. V of 2, and then 8. Over 4 minus 2. So that gives negative 3 over 2. The units, well, again, our velocity units here were feet per second. And the time units are in seconds. And so, yes, we'll end up with negative 3 over 2 feet per second squared. Okay, so we end up with an acceleration time unit, right? And so we do have an average acceleration here. But we calculated by using the average rate of change of the velocity. All right. Questions on any of that? All right, I really want to do this next one. Charlie, go ahead. Yeah. So what I was referring to here, so this is what sometimes, this is a common student error. When students see this average acceleration, they think, oh, average acceleration. I know my average formula. It's going to be a of 4 minus a of 2 over 4 minus 2. Right? That's what I see students make the mistake of when they see average acceleration. They go to a of 4 minus a of 2 over 4 minus 2. Okay? Which is not correct. Because when you do this calculation, you're taking an acceleration here and dividing it further by time. So you'll have like feet per second squared in the numerator here, divided by seconds. So you'll end up with like feet per second cubed, which that is not an acceleration unit. So you get the wrong calculation basically. When you do average acceleration, it's really velocity that you're subtracting on top, then dividing by time. Because by setting it up that way, velocity divided by time, you end up with acceleration units. You end up with an acceleration at the end. Does that help some? Okay, so that basically because it's just a common error that students make. Same thing with up here. In the previous one, right? Well, we talked about average acceleration here too. Same idea. And we noticed we used v for the average acceleration. Okay, so, all right. Does that help? Any other questions on that? All right. And again, if you guys want, please sign up for office hours. We can discuss it more because this is not easy stuff. Okay, so don't just assume because no one else is asking questions, you're the only one that's suffering, and you must be really just dumb, and you should probably not be in this class and all that stuff. Don't think of those things if that's what you're thinking, right? You just need to work on it more, okay? Or ask questions during class or come in during office hours, and I'll be happy to help you, okay? I think when we get through this number 11 here, I think that's, I also want to do 12 as well, but I won't have time for 12. So I'm going to go through 11 here, and then we'll, be done because I don't want to, oh, goodness gracious. Yeah, I don't want to go into your next class. I'm already kind of running long here anyway. Yeah, 9:50. I got 10 more minutes. Okay, we'll do this one more here then. Okay. Yeah, 9:50. Okay. All right, last one. The particle moves along the y-axis such that its position in meters can be modeled by this equation right here. Okay, where t represents the time in seconds. T greater than or equal to 0. Okay. Now, you look at this. Okay, and it's like pretty complex, right? So this one would be a calculator active question. All right, so we can use our calculator. So if you have your calculator handy, you might want to get that out. We'll take a look here. So first it says find the velocity and the acceleration function. Well, that's something we can do without our calculators, right? To find the velocity, oh, notice by the way, we're moving along the y-axis, and notice it's not x of t, it's y of t, right? So that's indicating that we are on the y-axis. We're moving up and down now as opposed to left and right. Okay, just indicative of that. All right, given this function, how can I find the velocity then? What do I need to do? Let's go to Josie. What do you say? If I have the position, I'll talk about that, Sam, in a second. Yeah. If I have the position function here and I want to find the velocity function, what should I do to this position function? What calculus-y thing? So it's not the slope formula. We just want to find the instantaneous slope, which is the derivative. Just take the derivative. That's all we have to do here. Yeah. So 12.06t, if I multiply by 2 there, plus derivative sign. Anybody? Cosine. Derivative e to the t. E to the t, good job. Yeah, okay. Easiest derivative of my life. All right, and then we'll do acceleration too. All right, so derivative of 12.06t, that's just going to be 12.06, right? Plus derivative of cosine. So this becomes negative 9 sine t. And then derivative e to the t again is e to the t. So there's our velocity and our acceleration functions. Find the initial position. So initial means at the start, right? And if we are at the start, what is our time? 0. So that means t equals 0. And the same thing for velocity, same thing acceleration. So we want to find y of 0. We want to find v of 0. We want to find a of 0. Okay, now let me show you some kind of magical stuff you can do with your calculators, especially if you have like one of the newer, nicer calculators kind of thing. I gotta minimize this. You guys get to see my messy desktop in a wedding photo. Very exciting. Yes, we had an AT at our wedding. Jealous? All right, so anyway, here we go. All right, So let me show you an alternative way to type in a function. I already showed you guys yesterday how to evaluate a derivative at a number, but let's type our function into y equals. So Sam, to answer your question, this is how you will be typing things into your calculator. Okay, you'll just use it like y equals instead. That's the y of t. We're just going to use y equals. We're going to use x instead of t. That's it. Okay, so I'm going to type in my function here, 6.03 x squared for t squared, right? Plus 9 sine of x, okay, minus, and then e to the x. So second e to the x and put an x in there, like so. Oh, my pretty print's gone now. That's right. I'm going to change it back. Math print. There we go. Okay, like so. There's our function. Now, we want to evaluate our function, right? We want to evaluate y of t at 0. So we want to find y of 0. A couple ways you can do that, right? You can go second graph. You can use your table, right? So 0, negative 1. Okay. You can also go to the graph itself. And anytime you have a graph, you can press second trace and use the value command. And then just type 0 in for your x and hit enter. And then there it is. At x equals 0, y equals negative 1. That's another way you can use your calculator to find the value of x at a particular, the y value for a particular x value. Let me show you something else, though. You can actually use y1 on your home screen. So if I press vars and then arrow over to y vars and function, you can see I can select y1. And now if I use a parenthesis and put a 0, like I'm plugging 0, like I'm using y1 as like f, and I plug 0, that's okay, Maya. I plug 0 into y1, it evaluates it at negative 1. Okay? So there's y of 0 is negative 1. Okay? Now the beauty of that, when I go to take the derivative, so let's now evaluate the derivative of y, which would be v prime of t, right? So this would be like, or this is like y prime of 0, which is equal to the v of 0 there. Math, and then num, and then, oh no, I'm using the wrong command. Sorry, math 8, n deriv. Okay, we're going to take the derivative with respect to x. I can now just type that y1 in here. I don't need to retype the whole function. I can just type, I can use that y1 command. So y vars function y1. And then I want to evaluate it when x is 0. So I'm going to now take the derivative of that function that I typed into y1, my position, and evaluate it at 0. And there it is. So 8. It's a rounding error. It should be 8. Okay? And what about, Mr. Wade, what about acceleration? Though I have to take two derivatives. Well, guess what? Math and deriv. I'll do it at x. And then inside here, I'm going to do math. This should work. Another n deriv. So you see I'm taking the derivative of the derivative. This is the second derivative, right? So I'll do the x again. Now I'll type in my function, vars, y vars, function y1. Okay? And I want to evaluate this one. Ooh, actually, this is going to be interesting here. I think if I just type in x there, actually, you know what? This might not work now that I'm looking at it. It might not work. We'll see. Let's see. I don't know if that's right. Let's actually plug in 0 here. So a of 0 would be 12.06 minus 9 times the sine of 0 minus e to the 0. So that'd be what? 12.06 sine of 0 is 0. E to the 1, so minus 1, so it'll be 11.06. Is that what we got here? Yeah, I guess we did. It did work. 11.06 if you rounded there. Okay. So anyway, that's how you can use your graphing calculator here to do this. You can actually use your graphing calculator to take the derivative and evaluate a point, right? You can type it to y equals, and then just use that y1, vars, y vars function, and then y1 like that too. Okay. What is the velocity of the particle when the acceleration is 0? So we have to find the velocity, but before we can find the velocity, we have to determine when is the acceleration 0. So we're going to set our acceleration equal to 0. Okay, but again, I don't want to solve this, so I'm just going to use my graphing calculator. So I will graph my acceleration here. I'm just going to turn off that one. 12.06 minus 9 sine of x minus e to the t, or e to the x. Okay, whoops, I don't need that. We'll graph. Okay, so here's where it's 0, so I'll press second trace and go to the 0 command, again, because we're just using our graphing calculators here. I'll go to the left of my 0 and hit enter, go to the right of my 0 and hit enter as well, and then you guess you just want to move that right in close to where the 0 is and hit enter. And the x value is about 1.255, we'll say. So that's the time when the acceleration is 0, but we want to find what is the velocity then. So then we'll finally v of 1.255, okay? And again, this is where I can use my graphing calculator if I want to and just take the derivative. If I go back to my home screen, remember that this command right here, right, that's the derivative of the position, so this should be velocity. I don't want to evaluate it at 0 though, I want to evaluate it at 1.255. And so it's about 14.423. Okay, and that would be t is time in seconds, and y-axis is just position, so it'd be like units per second or something like that. Okay. When is the particle moving up? Justify your answer. So again, moving up, that's a direction, right? And so we use the velocity to determine the direction there. Okay, so that's velocity greater than 0. So again, we can look at the graph of the velocity, and I will just go ahead and type that in here too, into my y3. So 12.06 t plus, oops, plus 9 cosine of t, or x in this case, right, minus e of t. Oops, I don't need to put parentheses there, right, sorry. So we'll graph this. Okay, and again, we might have to adjust our window here, but it looks like our velocity is positive, right, in this range right here. So from this 0 to this 0. So again, we just find the zeros. And sorry, I know my time is up here, guys. I apologize here. Almost done. Okay, so it looks like it starts at negative 0.578. The particle is moving up from negative 0.578 less than t, less than, and then let me get the last 0 here. And hit enter to 0, and 3.536. Okay, and because the velocity is positive on this interval. Okay, so there you go. All right. Thanks for sticking with me, guys. I know you got to get to your next class. I'm going to finish this recording, so I'm going to continue recording, and I will finish up this number 12, and I will post the entire video to our page. I will also go through number 12, though, too, at our next meeting on Monday as well, just because I want to make sure you guys get to see it if you don't watch the video or something like that. Alrighty. So yeah, there you go. Please make sure you check out the homework and stuff like that tonight. Yeah, we'll see you on Monday, or come into office hours if you want some extra help. I'll be happy to help. Okay. Bye, everyone. You're welcome. You're welcome. Yep, Charlie. Yep. Yep. Yeah, it should be, it's units per second. Not units per second squared, just units per second, because it's a velocity, so yeah. So velocity, right? So velocity and speed are very closely related, right? So when you think about speed, right, like miles per hour, right? It's a distance divided by a time. So velocities will also be a distance divided by a time. So then units per second. Okay. If you do velocity per second, right? Okay, Charles, if you do velocity per second, like we did up here, right? Here's velocity per seconds. That becomes feet per second squared then, which is an acceleration now you're talking about. Subtract the 5 and the 8, you get a -3. That's in feet per second because this is the -3 is velocity, but then you're dividing it by seconds, so it becomes feet per second squared. That makes an acceleration, which is why when you see average acceleration, it's really the velocities that you're subtracting on top, because you then have to divide by times, which result in a acceleration unit. Does that help some? And then are you planning on coming in during set or something like that? I forgot. They start at 12:30. OHS with support. Yep, a Google Meet. Yep. OHS with support. It's just a Google Meet. I'm here, and I just kind of answer any questions you have or whatever. We can talk about whatever you want. Until 3:30. Show up. I'll be there. Yep, I just host it. Sit there all by my lonesome. Twiddle my thumbs. Nah, I'm normally like grading and stuff like that, so. But yeah. That's right, but if you show 329 and you have like 50 questions, Charlie. Okay, 328, right? Okay, thanks. thanks. All right. Yeah, absolutely. And Charlie, if I am going too fast, please say something, okay? Because, you might not be the only person, and so someone's got to speak up at some point, so. What, you don't like listening to me talk? You don't like listening to me talk for an hour and 15 minutes? That bores you, you're saying? Yeah, right. Well, I promise I'm not taking it personally. I'm not hurt. All right, I'm going to finish. You know what? I'll go ahead and finish 12 because I said I was, but I'm going to go ahead and do it anyway. So, yeah, anyway. All right. See you, Charlie. 3:28 on the dot. 50 questions. See ya. All right, so sorry you guys had to watch all that. If you're going to continue watching here and finish this up, I do think though I'm pretty sure I wanted to finish this all up today. Let me just now check to make sure. So, oh man. Pretty sure we wanted to finish that up today. Yes, I know we're still recording. Don't worry. I promise you, listener at home. Oh, maybe I did go too far. Maybe I wasn't supposed to do all those. Whoopsies. Okay, well, I am going to stop now. Never mind. My apologies.